Today we're going to talk about related rates. I love this section. These questions have always been so much fun to me since I first studied calculus. So we're going to practice setting up and solving a particular kind of applied calculus problem, which is called a related rates problem. What exactly do we mean when we say a related rates problem? In a related rates problem, you have two quantities, both of which are changing over time. But those two quantities are related to each other in some way. One of my coworkers fills up his swimming pool every summer. And perhaps it's even one of these fancy commercial swimming pools, which in profile looks a little bit like this. You have some shallow end of the pool and then a slope leading to the deep end of the pool. Now, you're dumping water into this pool, and the water is coming into the pool at a certain rate. Simultaneously, the water at the bottom of the pool, that water level is rising. So you have two sort of related quantities here. You have the volume of water in the pool, which is increasing as you fill the pool up, and then you have the water level in the pool, sort of the height of the water. Now, both the volume of water and the height of water are changing over time. As you put more water into the pool and it's filling up, the water level rises. But the question might be, how is the rate of change of the water level affected by the rate of change of the volume? If I fill the pool at a rate of maybe 5 cubic meters per minute, how fast will that cause the water level in the pool to rise? That kind of thing. So in this video, I'm going to give you two examples, and I'm going to use them to demonstrate my general step-by-step thought process/technique for problems of this nature. Now, I know that two examples is not always very much, so I'm going to post to Canvas not only a bunch of other videos on this subject, but I'm also going to post some excerpts from other textbooks, lots and lots of examples that you can read or watch until you feel comfortable with this kind of problem. So, for our first example, in this case, we are pumping air into a sphere-shaped balloon. How fast is air being pumped into the balloon? The volume of air inside the balloon is increasing at a rate of 100 cubic centimeters per second, say. Now, as you fill the balloon with air, the balloon gets bigger. So, as the volume increases, the radius of the balloon is also increasing. So the question is, how fast is the radius of the balloon going up at the very moment when the radius is 25 centimeters? Now, when you're getting started on a related rates problem, step one is usually just to try and figure out what in the world is happening in this problem. They give you this huge paragraph full of different numbers and bits of data, and so step number one is just to try and wrap your mind around all this information. So usually what I like to do is start by drawing a sketch. We have a balloon, and one of the more interesting things about this balloon is that we're told that it's perfectly spherical. So this balloon has some radius called, let's say, r. The balloon also has some volume. Let's just call it v for short. Now let's try and figure out what some of the numbers in this problem represent. The first thing that I noticed that's interesting is that at the end of the problem, they're telling me that the radius is 25. So I'm going to make a quick note of that. Radius is 25. R equals 25 in mathematical notation. Looking back at the first paragraph, I can't find any information about what the volume is equal to. But I can see that the volume is increasing. The volume is changing at a rate of 100. Now, in problems like this, when you see words like rate or how fast, that's referring to the derivative of a quantity with respect to time. When they say that the volume is increasing at a rate of 100, they're telling you that if you take the derivative of volume with respect to time, that rate of change is 100 units. So that's the significance of the second number that's given to me in this introductory information. The next thing that I'm going to do is I'm going to try and figure out exactly which quantity in this problem they're actually asking me to find. What are they asking me for? Okay, so let's have a close look at this question in the second paragraph. How fast is the radius increasing? Just like the word rate, the word how fast is usually signaling a derivative with respect to time. How fast is the radius increasing? At what rate is the radius changing? So what is this problem asking for? This problem is asking for the derivative of the radius with respect to time. Okay, so I've now parsed this paragraph. We have a balloon which is shaped like a sphere. Sphere is a mathematical term, so that's important. So I'm going to make a note of that. The balloon is a sphere. The second thing, the volume is increasing at a rate of 100. So there's a quantity in this problem called volume, and its rate of change over time is given by 100. How fast is radius increasing? How fast is the radius changing? So there's a quantity in this problem called radius, and it's asking how fast, what is the rate of change of radius? When radius is 25. No rates, no how fast, just radius is 25. So r, with no derivatives, just r, is equal to 25. This is sort of the thought process that I use when I'm just trying to understand the question. Okay. Step 2, find an equation that relates the quantities in the problem. What often will occur is that the equation that you need is a geometric formula. For example, we were given the very important information that this balloon was spherical. And there's a formula for the relationship between the radius of a sphere and the volume. Now it's super easy to forget geometric formulas. When in doubt, I usually just Google it to see if I can find a formula which is appropriate. So for example here, the volume of a sphere is given to me here, which is 4/3 times pi times r cubed. And that formula is great because it gives me a relationship between the two main quantities in my problem, volume and radius. So here's an equation, V equals 4/3 pi r cubed, which relates the two quantities in the problem, radius and volume. So the next thing that we're going to do is we're going to take that equation from step 2 and we're going to apply the derivative with respect to t to both sides. And we're going to simplify that, being careful to use chain rule or product rule or whatever rule whenever is necessary. So the step that we're about to do is very similar to when we did implicit differentiation. Except this time, instead of taking a derivative with respect to x, we're taking the derivative with respect to time, a rate of change as time changes. Okay, so the derivative with respect to time of volume, I'll just write as dv dt for short. Constant multiple rule says that you can bring the 4/3 pi out and worry just about the derivative of r cubed. Now in this situation, the cube function is the outer function, and the inner function is r. So if I wanted to find this derivative, what I would write is the derivative of the outer function, which is 3 blank squared. I would fill the blank with the inner function, and then I would multiply that by the derivative of the inner function. In this case, dr dt. Okay, so we took the equation from step number 2 and we applied d dt to both sides. And we simplified that, being careful to use chain/product rule when necessary. Step number 4, let's take this equation from step 3 and fill in the values of basically everything that we can. Fill in the values of everything that you can until the only quantity that's left unknown in the equation is the quantity that you were asked for in the problem. For example, I was given the fact that the radius is 25. I was given the fact that dv dt was 100. What I'm trying to find is dr dt. So I'm going to scroll back down, I'm going to fill in the blanks of everything that I possibly can, and by the time I'm done, the only unknown left should be dr dt. So dv dt was 100. That was equal to 4/3 times pi times 3 times 25 squared. And the only unknown left is the dr dt that I'm trying to find. Now the virtue of filling in absolutely every unknown except for this one is that it is now super simple to just go into the equation and solve for dr dt. So I think if my arithmetic checks out, this is going to be equal to 100 divided by 4 times 25 squared, and pi is equal to dr dt. And the only reason I've written this in kind of this strange way is because I recognize that 4 times 25 is actually equal to 100. So that simplifies really nicely. Okay, so what is the rate of change of radius? It's given by 1/25 times pi. How would I interpret this result? I would say that the radius is changing at a rate of 1/25 pi at the specified time. If we want to be really careful, we can give this interpretation using units. Looking at this problem, I notice that radius is being measured using centimeters. And the only mention of a time unit in this problem is given here where it says cm cubed per second. So the implication is that time is being measured in seconds and radius is being measured in centimeters. So if you want to, you can use that information to make your final answer even more concrete. Radius is changing at a rate of 1/25 pi centimeters per second at the specified time. Let me give you another example of my method. So in this example, they say to me, okay, we've got a tank of water and it's in the shape of an upside down cone. This is important information. Cone is a mathematical term, and there are specific formulas associated with that. Now they go on to describe the parameters of this tank. Let me draw a quick sketch. I'm going to draw an upside down cone as specified. They tell me that the cone has a height. The cone has a height of 6 meters. And the cone has a base radius of 2 meters. So what they're doing now is they're describing the shape of this tank. Okay. Now this is interesting. Water is being pumped into the tank at a rate of 2 meters cubed per minute. So this is important. A related rates problem is about two related quantities, both of which are changing over time. And we were just given information about one quantity in this problem, which is changing over time. The amount of water in the tank, the total volume of water in the tank, is changing over time. So I'm going to say volume of water, maybe V for short. What they just told me is that the water is being pumped into the tank at a rate, so dV dt, a rate of 2 cubic meters per minute. Find the rate, so here's an important signal, here's another important signal, because they're about to tell us another quantity in this problem which is changing over time. Find the rate at which the water level is rising. Okay, so the second related quantity that is changing in this problem is the water level in the tank. This makes sense because as you fill the tank more and more, the height of the water will begin to rise. So the height of the water is another quantity which is changing over time, and that's called h. I'll just call it h for short. Now notice that they're asking us to find the rate at which the water level is rising. So the unknown quantity in this problem is the rate of change of the height. When the height of the water is 3. Height of the water is 3. So let's jot that down as well. The height of the water, no rate of change. The plane height of the water is 3. Okay, so now we have two related quantities, both of which are changing over time. The volume of water and the height of water. The quantities 6 and 2, the base radius of the cone and the height of the cone, are not the changing quantities in this problem. the quantities that we are concerned with are the things that are changing over time. Height of water and volume of water. Okay. So now what I need to do is I need to try and find an equation that relates the height of the water in the tank to the volume of water in the tank. And what I am noticing is that because the tank is cone-shaped, the water in the tank will also be cone-shaped. So I'm thinking that maybe the formula that I could use to relate the volume of water and the height of water is a formula related to the volume of a cone. So I guess we're on Bing now, that's fine. The volume is 1/3 times pi times radius squared times height. Now immediately there is a big difference between the equation that we have just found in this problem and the equation that we found in the previous problem. In the previous problem, the only related quantities that we were concerned with were radius and volume. And conveniently, our formula contained only radius and volume. In this problem, the only two quantities of concern are volume and height. Yet the formula that we found online has volume and height and radius. So let's see if we can eliminate radius. We don't care about radius in this problem, it's just in the way. The key with that is to use what's called similar triangles. I'm going to go back to this picture of the tank and I'm going to look at one half of it sort of from the side. We were told that the height of the tank was 6 and the base radius was 2. Meanwhile, for our little embedded water slice here, we're calling the height of the slice h and the radius r. Which means that we can use similar triangles to set up a proportion that would relate h and r. For example, we could say that if I take the side h and divide it by the big side 6, then that would be equal to the side r divided by the big side 2. So if I rearrange that, I would get that h over 3 is equal to r. So the radius is always the same thing as height divided by 3. If I substitute h over 3 into this formula, wherever r appears, then that will get rid of r and leave something containing h only. So h over 3 quantity squared instead of r squared. So after simplifying this, we get, I think, pi over 27 h to the 3rd power. Haha! Now we have a formula relating h and v, which doesn't contain any other quantities that aren't important for our problem. It only contains h and v. So now let's take that equation and apply d dt to both sides. So pi over 27 h cubed. dv dt then is equal to pi over 27. Then the derivative of the outer function, 3 blank squared, with h plugged in, multiplied by the derivative of the inner function dh dt. Okay, so then we need to take the equation, fill in the values of all the unknowns except for the one quantity which we're trying to find. So dv dt was actually given to us. dv dt was given as 2, and h was given as 3. So 2 is equal to pi over 27 times 3 squared, and the only unknown left is the quantity that we were asked to find. So 3 times 3 times 3 is 27, so this will simplify, and we get dh dt equals 2 divided by pi. Alright, that technically should have been in step 5, I suppose. Whoopsie. How, if I wanted to, how would I interpret this result? I would say that the height of the water is changing at a rate of 2 over pi at the specified time. Now, if you wanted or needed to add units to this answer, it looks like the units of height are given in metric in terms of meters, and I see a time unit here. It looks like time is given in terms of minutes. Meters over minutes. The rate of change. Okay, so this is my process. Once again, numerous more examples will be posted, and we will basically be spending an entire class day just practicing this, because you can watch as many examples as you want to, but there's no substitute for actually getting in and doing a problem like this on your own. That concludes today's material. We practiced setting up and solving problems that were called related rates problems, where you have two related quantities, both of which are changing over time.